Hi, this video describes a undirected graph adapter. We've presented two data structures that represent directed graphs, but sometimes we need to deal with undirected graphs. So what we're going to see here is how we can implement an undirected graph data structure using one or the other of those two directed graph data structures, the adjacency list or the adjacency matrix. So like I said, so far our adjacency matrix and adjacency list have stored directed graphs, but we also need a data structure for undirected graphs. We're going to use the adapter approach that we've used a few times already. An adapter is a container that uses a pre-existing container to implement a new different interface. So what we're doing in this video is using a directed graph data structure, and it could be the adjacency matrix or it could be the adjacency list. They both work, but we're using one of those to implement a new interface for an undirected graph. Let's define the operations we're trying to create here. So this is a different abstract data type. It's going to have a different set of operations to represent an undirected graph instead of a directed graph. So what I've done is written those operations here, and I've highlighted in yellow the changes that we made relative to the directed graph abstract data type. So we still have a create operation that creates a graph that has n vertices and no edges. The one change I had to make was change the word directed graph to say undirected. Vertex count and edge count work the same way. They return the number of vertices and edges respectively. Has edge is just slightly different because in a directed graph, has edge tells us if there is a edge from I to j, because there's this notion of direction on the edges. But in an undirected graph, the edges are bidirectional, they go both ways, so instead the word we use is between. So has edge ij returns true if there is an edge between I and j, and false otherwise. We make the same change to add edge ij adds an undirected edge between I and j, remove edge ij removes an undirected edge between I and j. The big change we made is to out edges and in edges. Those functions don't really make sense anymore. There's no distinction between an out edge and an in edge, so we've replaced in edges and out edges with a single function called adjacent. Adjacent of I returns a vector of every vertex j that is adjacent to I in either direction, because there is no difference between in and out. So to do one of these adapters, we have to define a correspondence between the concepts in the API we're implementing and the concepts in the API we're using. So we're creating an interface for an undirected graph. We're using an interface for storing a directed graph. We need a correspondence for the vertices and one for the edges. The vertex part is really simple. Every vertex in the undirected graph corresponds 1-for-1 to a vertex in the directed graph. The edges are just a little bit trickier. In an undirected graph, an edge can go in either direction. So what we do is for every undirected edge in the undirected graph, we create two directed edges, one going kind of forwards, the other going reverse. So two parallel edges going in opposite directions. So for example, the undirected edge between 1 and 4 is represented by, there should be two directed edges between 1 and 4, one going up and one going down. Better example might be between 0 and 3. There's an undirected edge between 0 and 3. So there's two directed edges going up and down between 0 and 3 in the directed graph that we store. So what I'm going to do now is define the name, data members, and constructors of the two data structures we're creating. We're creating an undirected adjacency matrix, and we're creating an undirected adjacency list. These things are different between the two, the name and the constructor data member, but from then on, all the other functions are identical, actually. It's the same exact code in both. So first, the parts that are different. We have our undirected adjacency matrix, and it only has one data member of a directed adjacency matrix. That's the data structure that actually holds all the information. The constructor for undirected adjacency matrix is given the number of vertices, and it just calls the constructor on the directed adjacency matrix with the same number of vertices. The same kind of thing happens with our undirected adjacency list. The only change I made from the previous slide was I changed every occurrence of matrix to be list instead. So the class undirected adjacency list owns one directed adjacency list, and the constructor for undirected adjacency list just calls the constructor on the directed adjacency list with the same number of vertices. Okay, so that's the end of all of the code that's different between the two classes. The rest of this code is the same for the two, so I'm just going to present it once. So the undirected graph vertex count is just equal to the directed graph vertex count, so that's a one-liner, return the directed's vertex count. The undirected graph's edge count is 1/2 of the directed graph's edge count. Remember that for every one undirected edge, there are 2 directed edges. So what we do is we get the directed graph's edge count and divide by 2. Note that this is always even, so there's no rounding problems because we're always adding pairs of edges into the directed graph. Has edge is really simple. There's an edge between I and j. If the directed graph has an edge from I to j, remember this is why we're adding both directions so that no matter what order I and j are passed in, this gets the correct answer. Adding an edge is pretty easy. To add an edge between I and j, we add one edge from I to j and a second edge from j to I. Those are the parallel edges. And then remove edge has to undo that. So to remove the edge between I and j, we remove the edge from I to j, and we remove the edge from j to I. Incident is new. Incident has to return the vector containing all of the vertices that are adjacent to I, meaning connected to I by just one edge. So out edges I and in edges I would both return the same information. We could call either one. It doesn't really matter. But in the adjacency matrix, both of those operations are big O of n. It doesn't matter which one we call. We could pick in edges or out edges. But in the adjacency list, out edges is substantially faster. Remember, out edges in the adjacency list just makes a copy of one of those adj lists. It takes big O of degree of I time. But in edges was big O of n plus m, and had to do the brute force thing of checking every single edge in the graph. So between the two, it's better to call out edges because out edges is going to be the faster operation for the adjacency list based undirected graph. So here's a summary of the runtimes. They're basically the same thing as what we have for a directed graph. So in an adjacency matrix, creating takes quadratic time, getting the vertex count, edge count, adding an edge, removing an edge, the has edge operation, those are all constant time because they're just matrix lookups, and the adjacent operation is big O of n. In the adjacency list, it's linear time to create, constant time for the vertex count or edge count or adding an edge, and removing an edge, getting an edge, or the adjacent operation are all big O of degree of I time.